Alright, so for the last part, we have a Bayesian model selection. For your reference, the model selection in frequentist scheme was essentially a combinatory optimization, right? In frequentist linear regression, the best model was the model with the highest AIC, a KK information criterion, because the AIC is built in a way that it both penalizes the model complexity and also the lack of fit. So the model that fits the data well but too much complex, which means that it has too many parameters, are penalized, and as well as the model that is simple but lacks the fit are also penalized. So that was the single metric that frequentist used to select the best model. So the model selection is the problem of combinatory optimization, because in the sense that for all possible discrete cases, because if you have p variables, then all possible set of models will be 2 over p, right? I mean 2 to the power of p, right? Which is over quickly over several thousands if you have many, several hundred thousands if you have many predictors, right? So the essence of the combinatory optimization is in combinatory optimization, finding a one true global optimum is quite very hard. It is nearly impossible. It's an NP problem. I don't know why it is called NP problem, but the NP problem is such a problem where it is possible to solve if you have an infinite amount of time and computational power, right? So to redress the problem in frequentist inference, the main techniques such as greedy algorithm, which is what we know as stepwise selection, or forward selection, backward selection. All these are the sort of a greedy algorithm for search for the local optimal, right? No, or we use the simulated annealing, or local search, or simulated annealing, or things like genetic algorithm. But in Bayesian setting, the model selection in Bayesian setting is done by Bayes rule, which means that we give prior for each of the possible model, right? And for each model, we calculate the likelihood of the data given the model, and we compare all the likelihood to get a posterior of the model, right? So in Bayesian model selection, we introduce another variable which is called z, right? Z determines whether a specific beta is 0 or not. For example, if you set beta, if you set the way things go like this, right? Let's say you have beta 0, beta j is actually a product of it has to be j, j and bj, right? So bj is a usual, bj is our standard, a familiar beta slope coefficient, but zj is a newly introduced latent variable, which is either 0 or 1. So selecting all model is to select a non-zero beta coefficient, right? This is equivalent. So if you have 5 variable, 5 possible candidates, right? 5 possible slopes, and if your z vector are like this, then your model is this. Right? This, in a sense, that if you give a prior on this random vector z, then we are essentially giving a prior on a possible set of models, right? So in this sense, that we have effectively introduced a new random variable z, right? And the role of the z can be summarized in this diagram. So z is a hidden variable. It's a random variable that affects the generation of the beta, right? And beta is in turn affected by the sigma squared and g prior, as well as the z, right? And that in turn affects the yi, which is the observation. So in this flow of things, we can write the joint density, and we can decompose the joint density in this way. First, we give a prior on PZ, right, and then independent prior on sigma squared. These two are not related, and also because we are implicitly assuming that the variance are all equal over all possible models. So and then beta are affected by the sigma squared and z, and finally we have the likelihood here. So how do we do inference on z, right? How do we get a posterior on z given data? That is simple. We just use Bayes rule, right? We just use the same old Bayes rule, right? In the Bayes rule, we can say the posterior probability of specific z is a product of a prior and the likelihood denominated by maybe divided by this thing right here. But this constant, which is a constant, right? It is a constant because we are summing over all possible models. But this one is impossible to calculate, because for this one to be calculated, we have to evaluate every likelihood for every model. We have to evaluate likelihood for each of every model, because that is impossible, right? Because there's so many models. So instead we just focus on getting this quantity, right? The prior on z, and we just focus on that this posterior is proportional to prior and the likelihood productive, right? So, and if we give a uniform prior from PZ, right, which means that we do not favor a specific model to another model, right? We just give equal, belief in every possible set of models. And if that's the case, then the PZ right here is proportional to be 1, and it's going to be cancelled out. So we're going to end up with the posterior that is proportional to, this one, right? This likelihood. So if we can calculate the likelihood of each model, then we can, approximate the posterior of the model, right, of the z. So in order to do this one, to get this one, we're gonna have to we have to start from the likelihood, and we're gonna have to average out the beta and sigma squared, right? So this thing can be decomposed into this one, right? Which is easy to see because z and sigma squared are not dependent, they are independent. So sigma squared just comes out without z attached on the side, and we have oh my gosh, and this one can be decomposed into these two terms, and in turn this can be decomposed into beta given sigma and the likelihood. And that is what I have wrote here, right here. But this term goes right in here. But I have subscripted this beta with z because the beta given z, right? The distribution of the beta, the beta given z is actually equivalent to a set of parameters that are not annihilated by that, where the corresponding z is not 0, right? So for example, like in this case, the beta would be beta 1 to beta 5, but beta z conditional on this specific z would be just the surviving beta 2 and beta 4. And that's actually the same, and that is similar for the xz or pz. Xz is a design matrix where only the selected columns are present, and also the pz is the number of the present betas in the regression in a specific model, right? So, and if you look at this term right here, this is actually if you just disregard z for a moment, then then this one is the marginal likelihood of y given sigma squared, which we have already derived in the previous slide. to be this one. I mean, as this one, right? Our answer is already given here, so we can just use this result right away, right? But the difference is that since in our case this is dependent on z, then the dependency would be reflected on this term and this term, because the sum of square residual are dependent on the choice of the predictive variables, which are determined by the form of a model, and also the total number of predictors are also would be this one, right? So this should be written as SSRG GZ, and the result is that we have this term right here, right? And this one is actually from this term. And if you integrate this term with respect to sigma squared, you can easily see that this density has a form of inverse gamma PDF. So we only need to know the inverse of inverse gamma PDF, right? So from this step into the next step, we have used this fact right here, and at this stage we have used the fact that this is the PDF proportional to PDF of the inverse gamma, and as an end result we are only getting this quantity right here. So the bottom line is that the marginal likelihood of any model, right? The marginal likelihood of a model is proportional to a quantity that can be written as this one, right? So for each model, the quantity, the PZ will be different for each model, and as well as the SSRG Z will be different for each model. So if you like, for any given two model, if you compare the ratio of the likelihood, then you can see whether if this value is bigger than 1, then the Z1, the first model, Z1 model is more favored by the data, and that decision is affected by these two terms right here, right? So in this equation, right, in this expression, this term, the role of this term is penalizes model complexity, because if the Z2 model, the second model, has more parameters, then this value will be positive, and it's gonna be a large, it's gonna be above 0, and it's gonna be large, then as a result, it's gonna this quantity will favor the first model as well. And aside from that, this quantity right here, this fraction right here, this term rewards model fit, the fit of the model to the training data, to our data. So if the second model fits data well, then the first model. Then since this term is positive, then this term would be would increase as the fit of the second model improves, right? Oh, I made a huge mistake here, actually. No, this is wrong. I have to fix something right here. There should be negative sign right here. There should be negative sign. Yeah, of course, because wait, this one. Let me pause right here. Oh, I made a stupid mistake. The sum of square residual the sum of square residuals represent the lack of fit, right? So if the second model lacks the fit, right, does not fit the data quite well, then this quantity would favor the first model, right? So this sort of a base factor we use right here is to illustrate the illustrate what Bayesian model selection does, right? So analogous to the AIC, the role of the AIC in frequentist model selection, in Bayesian model selection, this this sort of prior and posterior, this sort of model selection using the prior Z and the posterior Z somehow works in a same way as the frequentist one. Now, this model selection scheme favors the model that is concise, which means less parameter, and also the model that at the same time fits the data well, right? Which means less of a sum of scarce residuals, right? So how do we do this, right? So we're gonna have to use so it is now, since we do not know the exact density of this the posterior, we're gonna have to use Gibbs sampler. By using Gibbs sampler, it means that we're gonna have to for each of the random element, for each of the zi element in the z vector, we're gonna derive the full conditional posterior, all right? And we're gonna sample zi from this value, and we're gonna do this full conditional sampling for each of the z vector. And then as an end result, if we update the entire the vector, then we effectively get a sample from this one, right? This full posterior. So what we need to know is the conditional distribution of one specific z given all the other specific value of z and the data. And then since the zj, it's so hard to pronounce z. Since the zj is a binary, right? It has a binomial distribution. It's either 1 and 0, right? This density is easy to get, right? This probability can be expressed in this way, right? And if you divide the numerator and denominator by this one, then you get 1 plus oj, the old of j, over 1, right? Where this old of j means the conditional odds that zg is 0, which is a ratio of this one, right? Because the probability of z is 0 over 1 is proportional to this. If you use a Bayes rule, it's proportional to this quantity, where the denominator were cancelled out in both sides, right? So and since we have given a uniform prior for each of the zj, so that is equal to 1 over 2 and 1 over 2, it is gonna get cancelled out, and we are left with this one. So the essence is here this, right? So the Gibbs sampling mechanism for sampling model z proceeds like this one. For first the step 1 is that you somehow get an initial estimate of z, initial point z, which is for the convenience to be a model that includes all the possible variables, right? So step 2 is the Gibbs sampling. Update for each zj. So for example, for z1, right? So say you have you change the value of the z1 from z1 star, for example, the 1 to 0 or 0 to 1, right? And if you do this and you compare the marginal likelihood of the unchanged model as opposed to the marginal likelihood of the changed model, right? And you get a ratio, and you get a ratio of these two quantities. And with this quantity, using these quantities, you get you get the probability z3 is z3 star, or 1, given the data in other variable, right? And with this probability, you generate, let's say if this is 0.3, then you update zj to be 1, right? With the probability of 0.3, and you set this to be 0 with the probability of 0.7, right? And you can just repeat these sequences, this procedure for every element of the z, and the end result the end result is and the all the another random vector, another model G, where each of the variable will switch or not depending on the result of this probability, right? Depending on the probability, is in fact a sample from the full conditional, a full posterior, right? So we can easily, so if you say once you have these samples of model, right? Once we have like 10,000 of this model, right? Then for each model we can easily calculate, which it is easily sample set the square root and beta, right? Usually because we have given a G prior for this beta. We know without having to use Gibbs sampler, we know the full joint posterior of these quantities, right? So for each of the model we calculate all the beta and sigma squared, right? And if you take an average of all the beta right here, all the beta across all the models, then you get a Bayesian model averaging estimator of the parameter, right? I don't know if I remember correctly, but yeah. Oh. Precisely say to say it correctly. First you have to select a subset of best model based on its posterior probabilities, and for each of the variables, for each of the beta, we use the Bayesian model averaged estimator. For example, like as a result, you get two slopes. If you decide, so given this posterior probability, if you decide to use only this one and beta 1 and beta 2, then you can use this the new estimate for the beta. I mean, in a true Bayesian sense, you have to get a posterior density of this beta, given the data, right, under the model, under this specific model, right? But instead, you can just substitute a Bayesian model average, which is the average of all the sampled beta, all the sampled beta for each of the model, right? You get an average of all this one. So the performance of the Bayesian model averaged estimator as opposed to the maximum likelihood estimator are well introduced in our textbook, right? Maybe in the last section, I guess. So that was the scheme, the overall picture of the Bayesian model selection. And in this code, right in this part, I'm going to demonstrate you how we do this by running some codes on my computer. Okay. So we have a diabetes data right here, and so this diabetes data has it has many columns, right? So if you see, we have information. What was the it has over 64 predictors, right? If you do a Gibbs sampler model selection for something like this many variables, it will take a lot of time. So for the purpose of demonstration, I would only select the first 9 variables, right, to as our predictors, right? So this part right here is a code for calculating the log of marginal likelihood, right? This code is here is for the this quantity, this one, right? So where's the one note? The first function here, what we are doing with this function is to get the log of the marginal likelihood given the data, right? And for the The rest, once you set this function, then all you need to do is just set up a MCMC chain and start it, right? So for the initial estimate, we use this all possible model, this all inclusion model, right? This is our initial starting point, and we set the log likelihood of these initial points as LPY current, LPYC, and for each iteration, we randomly choose and we go through the possible predictors, Z1 to ZP, in a random order. It doesn't have to be random, but I guess it's a customary to use a random order inside each Z, right? Instead of just going from left to right. So from this random sequence, right, in this random order, for each of the, we're gonna tackle each of the element of the Z. So we're gonna switch the ZP is a proposed model where the to J's element is changed, right? And so we calculate the log marginal likelihood of the proposed model, and we compare it, right? And we compare this, we take a ratio of this, the log ratio, which is the log difference. We take a log difference of it and plug it into the equation right here. In that case, and after that, we get the update probability, right? Which is here, which is this one. And this formula right here is itself the full conditional distribution, right? This thing is the full conditional distribution, which is this one, right? So, but the funny thing here is that we have some adjustment for the sign, right? This is because, well, the sign, the LPYC, because what we have to get is what we have to calculate, what you like to calculate is the marginal likelihood of Y when a specific value of Z is 0 or 1. But this thing it could be stored in either LPYC or LPYP, depending on whether you are changing your model from 0 to 1 or 1 to 0, right? And this term is an adjustment for the term. For the detailed explanation I have included in here, you can just read it here, read through the passages, right, and get an idea of what I'm talking about. So, and the end result, if you run the code here, you just run this code. It's going to take a some amount of time. So, and if you add more, predictors, it's going to take longer. And I have included the code here, right here, so that every 100th iteration it shows the result. It shows every 100th iteration, and we discard the initial part and initial first half of the sequence for first half of the chain to mitigate the effect of the initial starting point, which was arbitrary. And we get a column mean, and we get an overall proportion of 1. Then we get this quantity, which can be said as a probability, of a marginal probability that a one beta of a single beta is included in the model or not. So if you can see, if you see this, that the beta 3 is heavily favored by the data, but the let's say the first predictor is not very much favored by the data, because this marginal posterior which marginal probability of being included in the model is very low, right? So we can summarize this result neatly in a diagram, right? Which I'm going to show right here. So this is from another set of data. This is from the crime data set, which is available in Kaggle or UCI, Machine Learning Repository, I guess. This is the result. It was actually a part of the final projects that I've done, that I did 2 years ago, maybe, I guess, and and we did a Bayesian model selection for the crime data. And for this predictor, for this y target variable, we had multiple, we have so many predictors, and we have to choose over 80, or we have to choose which model to include in the final model. And this probability is the probability that I've shown you earlier, right? It's the proportion of the times that each of the predictor were included in the samples that were generated by the Gibbs sampling. And if you set arbitrarily, the cutoff point, right, then you are left with the subset of subset of the variables, the predictor variables, right? And this is the Bayesian model average estimate for each of the beta, right? And this matrix right here is a plot that I've devised to visually deliver what Gibbs sampling does in model selection. So, for example, for each of the iterations, so every column represents each of the iteration, and in each of the iteration, the colored one means that this predictor is included, and the blank one, the empty one, means that this predictor is not included in the model, right? So if you can see, you can visually see, instead of just showing these bar plots, you can visually see that you can clearly see that there's a somewhat noticeable demarcation between these variables and these variables, right? Then these variables are heavily, are mostly favored by the data, whereas these other variables are not very much favored by the data. And the Bayesian model average, as opposed to the ordinary least squares, does not show a stark or some surprisingly remarkable difference, because the reason is that, as I said before, is because we have used the uniform prior for G prior, right? Which is a G prior. So in Bayesian, whether you do Bayesian estimate or Bayesian inference or the frequentist inference, the actual difference in results could not be very much different. But the difference is that if you have used the ordinary least squares method, which is the frequentist method, then you are only left with the one single optimal estimate of beta, along with the one single optimal point of optimal point of model. Then you cannot really answer questions like what is the probability that this model is correct or is favored by the data, or what is the probability of this specific of the beta lies within a specific range of interval, right? But if you use Bayesian linear regression and use Bayesian model selection, since the entire inference is based on the posterior distribution of beta or model, you can easily answer questions that requires you to convey uncertainty in your conclusion. So that's it for today, guys. So that's it for the Bayesian linear regression under 10 slides. So the contents are all summarized in 10 slides, but the video was quite long, I guess. So I hope you enjoyed the video. So if you like more videos from me, then leave a like or leave any feedback. For any comments, whether it is positive or negative, is very much welcomed by me. So I'm gonna upload another video relatively soon, right? I guess. So thank you.